In the first part of this video lecture, we have seen the definition of the integral restricted to a subset of the sample space. We have seen the fundamental theorem of calculus now applied to the Lebesgue integral with respect to the Lebesgue measure on the real line. And now we'll discuss the notion of the pullback of an extended BOREL function. So suppose we have a map that takes points from omega 1 to points of omega 2, and on omega 2 we define a BOREL function. Then in this case we can define a function on omega 1 by simply taking the composition. So we can define a BOREL function on omega 1 that simply assign to each little omega what would be the value of g of f of that omega. So that is basically saying if we have one space, another space, and on that space we can define a number, a function of it. You can think of it as a random variable, for instance, that gives it a number. Then we can define directly a function that goes from omega 1 and takes values as numbers by commutativity, simply by defining it from this path. Going now to this diagram we have been building, and the diagram stops here. It is already sophisticated enough. We have a function that maps points from a sample space to another sample space, and we can use that function to define the pullback of a given sigma algebra on the second or the target sample space. So we start with a sample space, another sample space, a function between them. We start with a sigma algebra on the target sample space. We can define the pullback of that sigma algebra. This we can define. This was not given to us. We can define. It was given to us maybe a measure on the source space, and we can use it to define a measure on the target space, which we call the push forward of that measure, again by the same function f. And if it was given to us a BOREL function defined on the target space, this will give us a BOREL function defined on the source space by simply composing that function with f. So this is again a pullback. So we can make pullback of a sigma algebra, and we can make a pullback of a BOREL function, and we can make a push forward of a measure. The previous definition was intended just to state now this theorem, which talks about how can we integrate a function, a BOREL function, that is defined on the target space, omega 2, with respect to the push forward of a measure that is defined on omega 1. So mu is a measure on omega 1. F star mu underscore star, F subindex star mu is the push forward of mu, so it's a measure on omega 2. So it makes sense to use this measure to compute an integral on the space omega 2 of a BOREL function g on omega 2. And the theorem says this is the same if we stay on the space omega 1. We use the original measure omega 1 instead of the push forward, and instead of pushing forward the measure, what we do is we pull back this BOREL function, define it on omega 1 and integrate it on omega 1. And the theorem is saying if one of these two integrals is defined, meaning it doesn't give plus infinity, minus infinity, then the other is also defined, and these two, they are the same. To prove this theorem, we're going to again consider only the case when G is the indicator of some event A, for some A measurable set on the target sample space. And later on, next week, we'll see a very standard and convenient tool that allows us to bootstrap properties that hold for functions that take two values, binary functions that only take value 0 or 1. And a measurable function that only takes value 0 or 1 can always be written as the indicator of a measurable set. So for now, we're going to focus on the case where g only takes 2 values, which means g is the indicator of a measurable set. And, well, what is the integral, the Lebesgue integral, on this measure space omega 2 with respect to the measure push forward of mu? Well, by definition, by the unitary property of integral, this is the measure push forward f star mu of the set A, and by definition, the measure push forward mu of a set A is nothing but the measure mu of the pre-image of A. On the other hand, if we now look at the source sample space, and there is this function, the pullback of the indicator of A on the sample space. And what is it? This is simply the indicator of A composed with this function f, and the integral, now again on omega 1, with respect again to the same measure mu. And this composition, what is this composition? This is again a function that only takes 2 values, 0 and 1, that will not change. What changes now is where does it take value 1? And it takes value 1 exactly at the set of points, the pre-image of A. So this is the indicator function of the pre-image of A under the function f. This is a function defined on omega 1 against this measure mu. And now by the unitary property of the measure mu, this is the measure of f minus 1 of A, which, since it coincides with what we did expanding the first integral, this would conclude the proof of this theorem.